Howdy folks, welcome back. So in this video, final video for this course, I'm just going to quick go through the practice final and again show you how I would go about solving the problems. Again, I recognize it's by no means the only way, and in some cases it might not be the way that works best for you, but if you're curious as to where to start, I'm just trying to give you an idea as to how I would go about solving the different types of problems, because that's kind of where I have the knowledge of there is how I would go about doing it. If you have another way that works best for you, I am excited to see that. But yeah, this is just kind of how I would go about doing that. All right. So again, you can find this exam on the coursework page, so on the assignments page, on the Pearson website there. All right. So yeah, so this first question here is looking at graphing a feasible set. So the final is cumulative, so it covers everything from chapter 1 up through chapter 9, with I think chapters 5 and 6 were skipped. So 5, 6, and 7 maybe. Yeah, I think we got 1, 2, 3, 4, 8, 9. Yeah. All right. So yeah, so this first one is looking at stuff from chapter 1, so looking at the feasible set. So the feasible set are those values that match both inequalities. All right. So we have 4x plus 7y is greater than or equal to 14. And we have x minus 2y is greater than or equal to 6. All right, so my first step is I would rewrite both these in slope-intercept form. So to do that, we're just going to solve for y. So we just want to get 1y all by itself here. So to start off, we can subtract the 4x from each side. And then we can divide everything by 7 for the first one here. So we have negative 4/7 x. This is y is greater than or equal to negative 4/7 x plus 14/7, which is 2. All right, same idea here. So here we have, we're going to subtract an x here, and then we're going to divide everything by negative 2. Now again, remember when we divide by a negative number, we have to flip the inequality symbol. So here we're going to have y is less than or equal to, this would be 1/2 x minus 3. All right, so then we're just going to graph these guys. All right, so I'll go ahead and use red for this first one here. All right, so I'll just fill in some values here. Two, -4, -6, -8, 2, -4, 6, -8, 2, 4. All right, so the first one I'll do in red here. So we have a y-intercept of 2. So that's right across the y-axis. And then we have a slope of negative 4/7. So to find my next point, I can go down 4 and then over to the right 7. So 1, 2, 3, 4. So that would be at negative 2. And then we're going to move over to the right 7. So I can connect the dots from there. All right, and then you're just going to choose a test value in either interval. So this splits my plane in half here. All right, so again, if I can do the origin, most of the time I like to do that just because it's easy to plug in. So when I plug in 0 in for x and 0 for y, either this one or this one, we have 0 is greater than or equal to 14, which is not true. So again, you shade the part that doesn't work. So shade in the part that involves that value. All right. And we'll stick with the festive mood here. So I'll go ahead and use green for this next one here. So we have y is less than or equal to 1/2 x minus 3. So there we have a y-intercept of -3. And then we have a slope of 1/2. So the slope of 1/2, again, slope is rise over run. So that means I move up 1, so up to -2, and then over 2. All right. And then again, you can connect the dots there. And again, you choose a test value in either interval. So again, you can go ahead and choose the origin if you'd like. So here, if I plug in 0 for x and 0 for y, I get 0 is greater than or equal to 6, which is also not true. So again, you're going to shade in the part that includes that point, because that's the part that doesn't work. All right, so our feasible set is just going to be this kind of triangle shape here. All right. So start off, we have a line. And since they're both, they could equal the values, so since they have a line underneath the inequality symbol, we are going to use a solid line here. All right. So we have 1 point is at 2, 0, and the other one is at -2, 7. Or yeah, 7, -2. All right. And then we're going to shade in the part underneath the line there. All right. And then we're going to do the next line. So we have 1/2 x minus 3. So we have 1 point is going to be at -3. There we go. Up 1, oh, over 2. All right. So that is our feasible set there. All right, so the next part is dealing with just kind of setting up a linear programming problem. So you have a candy shop puts together 2 prepackaged assortments to be given to trick-or-treaters on Halloween. Assortment A contains 3 candy bars and 3 suckers and yields a profit of 50 cents. Assortment B contains 2 candy bars and 3 suckers and yields a profit of 30 cents. The store has 500 candy bars and 600 suckers. Use this information to complete parts A through E. All right. So the first one is just kind of filling in the chart with, so just kind of reading the problem and filling in the chart with the appropriate information there. All right. So you have assortment A contains 3 candy bars. Assortment B contains 2 candy bars, and there are 500 candy bars available. And assortment A has 3 suckers. Assortment B contains 3 suckers as well, and there are 600 suckers available. And assortment A gives a profit of 50 cents, and assortment B gives a profit of 30 cents. All right. So yeah, so once you have the table, you can kind of set up. So X is the number of A assortments and Y is the number of B assortments. So just kind of setting up my inequalities, so my constraints here. So you have 3x plus 2y has to be less than or equal to the total number available of candy bars. And we have 3x plus 3y has to be less than or equal to the total number of suckers there. All right. And again, we can't have negative amounts of candy bars or suckers there. And then the earnings is going to be 50 cents times x plus 30 cents times y. All right. So yeah, so that's kind of where I'm going to leave it with regards to the problem on the exam. In this case, it does have the extra one of graphing the feasible set. All right. So yeah, so we have 3x plus 2y is less than or equal to 500. So we have 3x plus 3y is less than or equal to 600, so we can divide everything by 3 there. So that means when y and x-intercepts are going to be at 200. And then we're going to shade the part that's not included in there. So yeah, so that eliminates D. So D is eliminated right away there. Right. Of course. So we have 500. So finding my intercepts, so we can find the x-intercept by plugging in 0 in for y. So we have 3x plus 2 times 0, so 0 is equal to 500. So we have 500 divided by 3. It's going to be my x-intercept. So that's 166. So that eliminates B. So we have C and A here. And then my y-intercept. Yeah, it doesn't go through the origin. So yeah, so it looks like A is going to be our final answer. Again, that part doesn't really matter as much because, again, on the exam, I'm just going to focus on these top 3 or 4, I guess. All right. So yeah, so again, why you worry about these feasible sets is the vertices of these feasible sets are going to be solutions to your linear programming problem. All right. So yeah, so if I have the feasible set here, so you have y equals -1/2 x plus 4. Here we have y equals -x plus 6. Right? So yeah, so we got to find our vertices here. A, B, C, and D. All right, so A, B is going to be kind of the more difficult one to find. C is going to be relatively easy, and D is going to be relatively easy. All right, so we can start with A. So A is the y-intercept of this first line here, which my line is in slope-intercept form. So the y-intercept is going to be 4. So we have x is 0, y is 4. B is the most difficult one, so we'll come back to that. C is going to be the x-intercept of this line here. So to find your x-intercept, you set y equal to 0. So you have 0 equals -x plus 6. And we'd add an x to each side, so we get x equals 6. So you have 6, 0. And then D is going to be your origin. So that's going to be 0.00. All right. So now B is where these two lines intersect. All right. So since we have the y values have to be the same, that means that these expressions also have to be the same here. So you have -1/2 x plus 4 is equal to -x plus 6. So here we can subtract the 4 from each side, add x to each side. So you have 1/2 x equals 6 minus 4, which is 2. So you can multiply both sides by 2. So you have x is 4. And then your y is going to be what you get when you plug in 4 into either one of these. And you should get the same value for y, which I think we both get 2 for each of those. All right, so you have 0, 4, 4, 2, 6, 0, and 0, 0. All right, and then my objective function is to maximize 5x plus 4y. So I'm just going to plug in each of these values for x and y in my objective function, and I'm looking for the one that gives you the largest value. So you have 5x plus 4y. So I plug in 0 in for x and 4 in for y. I end up with 16 for that one. When I plug in a 4 in for x and a 2 in for y, I get 20 plus 8, so 28. When I plug in a 6 in for x and a 0 in for y, I end up with 30. When I plug in 0 in for x and 0 in for y, I end up with 0. So yeah, so in this case, the one that maximizes my objective function is the 0.60 or point C there. All right. So yeah, so that's kind of dealing with the graphical approach to solving linear programming problems. The next thing we talked about was the simplex method. So a matrix approach to solving these linear programming type problems there. All right. All right, so we have our simplex tableau here. All right. And so to go from one simplex tableau to another, we go through this process known as pivoting. So yeah, so the next question here is dealing with pivoting about the different elements. So for the first part, we're going to pivot about the 4. So on the exam, I'm just going to have you do 1 pivot. So you're not going to have to worry about doing 4 pivots and then choosing the one that fits there. So I'm just going to have you do 1 pivot. Unfortunately, I didn't think that far ahead when I was creating the practice exam. So yeah, so now I'm going to be going through all these pivots here. All right. So to pivot means I want to get a 1 in that entry and a 0 everywhere else in that column. So to start off, I'm just going to divide everything by 4 in this first row. So we have over 1 over 4. So we get 1 there, 9/4, 1/4, 0, 0. And 72 over 4 is 2 over 4. It'll be 18. Yep. All right, and then we want to get a 0 everywhere else in this column. So again, I like doing this step by step. That way I don't get ahead of myself. All right, so I want to get a 0 and this entry here. So to do that, I'm going to take -1 times, let's see, row 1 plus row 2. So in this case, the first row is going to stay the same for each of these. So the first row is done. All right, so then we take a -1 times each of my entries and add it to the entry in the second row. So you have -1 times 1 is going to be -1, plus 1 is going to be 0. -1 times 9/4 is going to be -9/4, plus 1, which is 4/4. So that's going to be -5/4. -1 times 1/4 is going to be -1/4, plus 0 is going to be -1/4. -1 times 0 is going to be 0, plus 1 is going to be 1. -1 times 0 is going to be 0, plus 0 is 0. -1 times 18 is going to be -18, plus 14 is going to be -4. And then again, we also want to get a 0 here. So to do that, we're going to take 20 times row 1 and add it to row 3. So again, we just go term by term here. So we have 20 times 1 is going to be 20, plus -20 is going to be 0. Next one, so we have 20 times 9/4. So the 4 and the 20 will cancel, so that's going to turn out being 5 times 9, which is 45, plus the -22 is going to be 23. Then we have 20 times 1/4 is going to be 5, plus 0 is going to be 5. 20 times 0 is 0, plus 1 is 0. Then we have 0, 20 times 0 is 0, plus 1 is going to be 1. And finally, 20 times 18 is going to be 360 plus 0 would be 360 there. All right. So then to read off the solution, you're looking for variables where you have 1 in one of your columns and zeros everywhere else. And for those, you can just read straight across. So yeah, so you have x, y, u, v, and m. So you have x, y, u, v, m. So in this case, this corresponds to solution x equals 18. We have v equals -4. And we have m equals 360. And the other variables, so the variables that don't have 1 in one of your rows, zeros everywhere else in that column, you just set those equal to 0. So you have y equals 0 and u equals 0. 18, -4, 5, sorry, 0, 0, -4, 360. All right. So the next one is we're going to pivot about the 9. So we're going to pivot about the 9 in this row here. So again, start off, we're going to take row 1, divide by 9 in this case. All right, so that's going to get us 4/9, 1, 1/9, 0, 0, and then 72 divided by 9 is going to be 8. All right, and then the other rows are just going to come on for the ride for right now. All right, and in this case, we're pivoting about this column. So we want to get a 0 everywhere else in this column. All right, so again, the first row is going to stay as it is. All right, so we want to get a 0 in this entry here. So again, I'm asking myself, what do I need to multiply this number by so that when I add it to this number, I get 0. So in this case, that's -1. So we have -1 times row 1 plus row 2. All right. So when we take -1 times 4/9, that's going to be -4/9 plus 1 is going to be +5/9. -1 times 1 is going to be -1 plus 1 is going to be 0. -1 times 1/9 is going to be -1/9 plus 0 is going to be -1/9. You have 0 plus 1 is going to be 1. 0 plus 0 is going to be 0. And finally, -1 times 8 is going to be -8 plus 14 is going to be 6. All right. And then here we want to get a 0 in this entry as well. So we're going to take 22 times row 1 and add it to row 3. All right. So we have 22 2 times 4/9 minus 20. All right. So it looks like we have -10 and 2/9. All right. So we have 22 times 1 is going to be 22 plus a -22 is going to be 0. Then we have 22/9 plus 0 is going to be 22/9. And then we have 22 times 0 is going to be 0 plus 0. 0 plus 1 is going to be 1. And finally, 22 times 8 plus 0 is going to be 176. All right. So you have x, y, u, b, m. All right, so in this case, we set y equals to 8, v equals 6, m equals 176, and then we have x and u are going to both be equal to 0. All right. All right. So in this case, the next one is we want to pivot about the 1 in the second row, first column. So we're pivoting about this element here. All right, so in this case, the first, we don't need to divide by anything because it's already 1. So we have 0, 1, 0. And then we have 4, 4, 9, 1, 0. All right, so then we want, so we're pivoting about this element. So we're in this column. So we want to get zeros everywhere else in that column. So in this case, we're going to take -4 times row 2 and add it to row 1. So -4 times 1 is going to be -4, plus 4 is going to be 0. -4 times 1 is going to be -4, plus 9 is going to be 5. -4 times 0 is going to be 0, plus 1 is going to be 1. -4 times 1 is going to be -4, plus 0 is going to be -4. 0 plus 0 is going to be 0. And then we have -4 times 14. 14 times -4. So we have -56 plus 72. So we get 16. Second row is just going to stay as it is. All right, and then we want to get a 0 here as well. So to do that, we're going to take 20 times row 2 and add it to row 3. So we got 20 times 1 is going to be 20, plus -20 is going to be 0. 20 times 1 is going to be 20, plus the -22 is going to be -2. You have 0 plus 0 is going to be 0. 20 times 1 is going to be 20, plus 0 is going to be 20. And 20 times 0 is going to be 0, plus 1 is going to be 1. And finally, 20 times 14 is going to be 280. All right. So you have x is going to be 14. U is going to equal 16. And m is going to be 280. And then y and v are both going to be 0. All right, so the last one here is we're going to pivot about in the one in the second row, second column. So we're pivoting about this guy here. All right, so again, first part, it's just going to stay the same since again we're dividing by 1. So we're divide the second row by whatever your pivot element is. All right, so we're pivoting about this column here. All right, so we want to get zeros everywhere else. So to start off, we can take -1 times row 2 and add it to row 1. So we have -9 times 1 is going to be -9, plus 4 is going to be -5. -9 times 1 is going to be -9, plus 9 is going to be 0. All right, then we have -9 times 0 is going to be 0, plus 1 is going to be 1. -9 times 1 is going to be -9, plus 0 is going to be -9. 0 plus 0 is going to be 0. And finally, -9 times 14. All right, plus 72. Oh, plus 72. -54 there. And finally, we want to get a 0 here. So we're going to take 22 times row 2 and add it to row 3. So 22 times 1 is going to be 22, plus -20 is going to be 2. 22 times 1 is going to be 22, plus -22 is going to be 0. 0 plus 0 is going to be 0. 22 times 1 is going to be 22, plus 0 is going to be 22. We have 0. And then 14 times 22 is going to be 308. All right, so we have X, Y, U, V, M. There should be a 1 here, sorry. All right, so we have X and U and V are both 0. We have Y is 14. U is -54. And M is 308. So we have X is 0. Y is is 14. Yep. U is -54. B is 0. And M is 308. All right, so the one that led to the biggest change in M is the first one. So that is 4 there. All right. That's probably the longest question that we'll have on this here. All right. So yeah, so again, pivoting is kind of how you go from one solution to the next. All right. So you have X, Y, U, V, M. All right. So we have 12, 3, 1, 0, 0. 15, 1, 4, 0, 1, 0, 12, 6, 24, 0, 0, 1, 0. All right, so to find the next pivot element, so start off to pick the pivot column, you're going to go for the smallest negative number, so the one that's most negative in the last row here. So in this case, that's negative 24, so that's going to be my pivot column. So this is the column that I'm looking at. And then pick the pivot element, you're just going to take each of these entries in the pivot column and divide the entry in the final column of that row by that pivot entry. So you have 15 over 3 for the first one and 12 over 4 for the second one there. So that's going to give me 5 and 4, or 3, sorry. All right, and you're going to choose the smallest one that has the smallest positive value. So in this case, that's going to be the 4. All right. All right, so the next one here is looking at dealing with a non-standard linear programming type problem. So standard form for linear programming problem, it has 3 requirements. First requirement, the objective function needs to be maximized. So in this case, we are trying to minimize our objective function, so that's kind of strike 1. The second thing is all your constraints need to be some linear polynomial less than or equal to some positive constant. All right, so in this case, we have a constraint where we have greater than or equal to some positive constant. So that's kind of strike 2. And the third thing is all your variables have to be relegated to values greater than or equal to 0, which in this case, we do check that off the list at least. All right. So yeah, so to convert it from a non-standard to a standard linear program type problem, we kind of fudged the rules a little bit. Specifically with regards to that second rule, where again, everything has to be less than or equal to some positive constant. All right, so to convert from non-standard to standard, you kind of have a little bit of a gray area where you just say less than or equal to some constant. Doesn't necessarily have to be positive. All right, so the first one is just fine, so we're just going to leave that as it is. So we have negative 6x minus 7y minus 2z is less than or equal to less than or equal to 4. But then this next one, since we have this greater than or equal to, we're just going to multiply both sides by negative 1. And again, remember when I multiply by a negative number, I have to flip the inequality symbol. All right, so when I multiply by negative 1, I just change the signs on each of my terms here. So we have negative 2x plus 6y plus 8z. And then we have less than or equal to. And then we have negative 8. And then finally, for the minimization, so to convert from minimization to a max problem, you're going to maximize, and you're just going to take negative 1 times whatever your objective function is. So again, you're just going to change the signs on each of the terms in your objective function. So in this case, my objective function turns into negative 6x minus 5y plus 6z. All right. So yeah, so here we have an example of looking at sensitivity analysis is kind of what it's known as. So we have a company manufactures paring knives and pocket knives. Each paring knife requires 3 labor hours, 7 units of steel, and 4 units of wood. Each pocket knife requires 6 labor hours, 5 units of steel, and 3 units of wood. Profit on each paring knife is $3, and profit on each pocket knife is $5. Each day the company has available 78 labor hours, 137 units of steel, and 105 units of wood. All right. So I'm going to go ahead and start with that. So yeah, so I'm not going to go through the whole process of figuring out the solution. So yeah, so this is how you can kind of set up the problem here. So you have X represents our paring knives, Y represents our pocket knives. So we have labor hours, steel, and wood. So we have all those constraints there. And we have our objective function. All right. And then there are several different sites that you can go to. There we go. So yeah. So this is Ian Math Help. So I just Googled simplex method calculator, and this is one of the results that showed up. So yeah, so you just type in your objective function. Yes, you want to maximize it, and you type out your constraints. And then yeah, we use the big M method. And then eventually it goes through the whole solution process, and this is your final answer. So the main difference is this first row here is the last row of how we write it. But other than that, it kind of gives you what you're looking for there. All right. So yeah, so that's how I got this here. All right, so this is my final simplex tableau for kind of the main linear programming problem. All right. Now, it says, suppose that the number of labor hours that are available each day is increased by 27. All right, so that corresponds to my slack variable u. So use sensitivity analysis to determine the effect on the optimal number of knives produced and on the profit. All right. So yeah, so when you do sensitivity analysis, you need to keep track of where your slack variables come from. So again, we have labor hours corresponds to my slack variable u. All right, so then you're just going to take the increase and multiply it by that entry in that column there. And you add that to the original value. All right, so same idea here. So we have plus 27 and negative 1 over 27. And we have plus 27 times 20 over 27. All right, so here the 27s are all going to cancel. So yeah. So y corresponds to my first column. So we have y is going to be 5 plus 7 is going to be 12. X corresponds to my second row here. So we have 16 plus a negative 5. So 16 minus 5 is going to be 9. And then I don't really care about the slack variable one. All right. So yeah, so the profit is going to be 73 plus 20 is going to be 93. All right. So X represents my paring knives, so that's 9. Pocket knives is my Y, so that's going to be 12. And the profit is going to turn into 93. All right. All right, so this is looking at the dual of linear programming problem. All right. So here we want to maximize 4x plus 2y, subject to the constraints given there. All right. So this is the solution for the primal problem. All right. So yeah, so we've already kind of gone through this in previous questions there. So yeah, so the maximum value again is going to be the final entry in the lower right-hand corner. So that's going to be 66. And you can just read across the rows here. So we have x equals 9. We have y is 15. And then for the dual problem, so your objective function is going to be the same. So for the dual problem, you're minimizing 60u plus 57v subject to, and let's see, it would be 5u plus 3v is greater than or equal to 4, and then 1u plus 2v is greater than or equal to 2. But that's not really important there. All right, so yeah, so you can find the solution to the dual by looking at the primal problem as well. So you can just read down the columns. So you have x is going to be 0, y is going to be 0. You have u is going to be 2/7. and V is going to be 6/7. All right, and then we kind of jump ahead to looking at chapter 8 and 9. All right, so yeah, so we are looking at transition HC, some Markov processes, and dealing with these transitions from one state to another. All right, so we have a transition diagram here, and we're to convert to a matrix. So again, we have from the columns to the rows. So the probability of transitioning from state A to state A, or I guess staying in state A, is 0.9. Again, just by looking at the diagram, we can tell that there. And then from state A to state B is going to be the 0.1. And then there's no line connecting A to C. So transitioning from state A to state C is going to be 0. Same idea here. So from B to A, we have 0.3. Again, just by looking at the diagram, we have that stays in B is going to be 0.2. And then from B to C is going to be 0.5. And then from state C, so once it arrives in state C, it's going to stay in state C. So we have 0, 0, and then 1. All right. All right, so looking at this, it doesn't really ask the question that I want asked anyway. All right, so we have for a certain group of states, it was observed that 60% of Democratic governors were succeeded by Democrats and 40% by Republicans, and 30% were succeeded by Democrats and 70% by Republicans. All right, so the first step is just setting up your transition matrix. So you have DR, DR. So Democrat to Democrat is 60%, so 0.6, and 40% by Republicans. So Democrat to Republican is going to be 40%. All right, from Republican, so 30% were succeeded by Democrats, so we have 0.3, and 70% by Republicans, so we have 0.7. All right. So yeah, so this is my matrix A. All right, so one way to find the longer term trend, I guess, is you can take powers of these matrices. So if you take A squared, that just means I'm taking A times itself. All right, so for the first entry, again, you just march across the rows down the columns. So we're going to have 0.6 times 0.6 plus 0.3 times 0.4. So we have 0.6, help if I turn it on. So we have 0.6 times 0.6 plus 0.3 times 0.4. So you have 0.48 for the first one here. All right, then for the second column here, we can use the second column of our second matrix, and again, we're going to use the first row. So you have 0.6 times 0.3 plus 0.3 times 0.7. All right, so you have 0.6 times 0.3 plus 0.3 times 0.7. So you have 0.39. And then for the second row entries, we can use the second row and again the corresponding columns of our second matrix here. So for the first column, we'll have 0.4 times 0.6 plus 0.7 times 0.4. So you have 0.4 times 0.6, 0.6 plus we have 0.7 times 0.4. 0.7 times 0.4. 0.52. And then we can take 0.4 times 0.3 plus 0.7 times 0.7. So we have 0.4 times 0.3 plus 0.7 times 1. So we have 0.61. All right. So now if we have our initial distribution, so we have x and y of 0. So then to find the transition after one generation, you can just take your a times your distribution. To find it after two generations, you can take a squared times your distribution. And then likewise, to find after 3 generations, you can take a to the third times your initial generation. All right, so that's just going to be a times a. So we have 0.48. So we have a squared, this is 0.52, and 0.39, 0.61 times a, which is 0.6, 0.3, 0.4, 0.7. All right, so for the first row, first column, we can just march across the first row, down the first column. So we have 0.48 times 0.6 plus 0.39 times 0.4. So we have 0.48 times 0.6 plus 0.39 times 0.4. So we have 0.444. All right, and then we can do for the second column, again, we can do the first row down the second column. So you have 0.48 times 0.3 plus 0.39 times 0.7. So you have 0.48 times 0.3 plus 0.39 times 0.7. All right, then we have 0.52 times 0.6 for the second row, first column, plus 0.61 times 0.4, 0.52 times 0.6, plus 0.61 times 0.4, 6. And finally, for the second column, we can do 0.52 times 0.3 plus 0.61 times 0.7. So 0.52 times 0.3 plus 0.61 times 0.7. 0.583. All right. So then to find, all right, I suppose I can fill in these values here. So we have 0.6, 0.3, 0.4, 0.7, a squared, so we have 0.48, 0.39, 0.52, 0.61. A to the third is we have 0.444, 0.417, 0.556, and 0.583. All right, so suppose all the current governors are Democrats. Assuming that the current trend holds after 3 elections, what percentage will be Democrats? All right, so to find after 3 elections, so right now our initial distribution is we have 100%, so we have 1 and 0% Republicans. So that's my initial distribution here. So then to find after 3 iterations, we can just take my a to the third times that initial distribution. So we have 0.444, 0.417, 0.556, 0.583 times 1, 0. All right. So we have 0.44 times 1 plus 0.417 times 0 is 0.444. And then we have 0.556 times 1 plus 0.583 times 0. So you have 0.556. And again, this represents Democrats and Republicans. So we have 0.444, which is 44.4%. All right. So we have these regular stochastic matrices. So regular and absorbing stochastic matrices we kind of focused on because, again, they have these long-term trends that we can determine. All right. So the first step in figuring out the long-term trend for regular stochastic matrix. So again, regular stochastic matrix is a matrix for which some exponent, so when you raise that matrix to a power, you get all positive entries. All right, so in this case, we have all positive entries right from the get-go. So then to find that stable distribution, you have x plus y equals 1. And then you have this times the matrix xy equals the matrix xy. So we're going to have 0.3x plus 0.2y equals x. And yeah, that's that one. All right. All right, so I'll just set up my system here. All right. So yeah, so the nice thing about these two variable cases is when we solve this, so we simplify this, we subtract an x from each side, we get negative 0.7x plus 0.2y equals 0. And here when we get a subtract a y from each side, we have positive 0.7x minus 0.2y equals 0. So these are pretty much coding for the same thing. So that means that we can ignore one of these. So yeah, so that's kind of the nice thing about these two variable cases, which is why I like to use the two variable examples, because you kind of have that trick that you can do. All right, so to solve this, we can just use substitution. So we can just solve for either x or y. So I'm going to go ahead and solve for y in terms of x, so we can subtract an x from each side. So we have y equals 1 minus x. All right, and then you can just plug in this 1 minus x in for y in your equation. So we have negative 0.7x plus 0.2 times 1 minus x equals 0. 0.7x. All right, we can distribute the 0.2 through here. So you have plus 0.2 minus 0.2x equals 0. All right, so you have negative 0.9x plus 0.2 equals 0. So we can do plus 0.9x. So we have 0.2 equals 0.9x, and you can just divide both sides by 0.9. All right, so we have x is equal to 2/9, and then y is going to be 1 minus that, so that's going to be 7/9. Or you can also do 0.22 and 0.77 repeating, yeah. All right, so we have 2/9, 7/9. All right, so then we have absorbing stochastic matrices. All right, so an absorbing stochastic matrix needs to have two requirements. So first of all, it needs to have an absorbing state. Second of all, it needs to have a way to get to one of those absorbing states. So in this case, we do have two absorbing states. So states A and B are absorbing because they have ones along the diagonal. So that's how you can kind of tell your absorbing states. However, we can't get to the absorbing states from state C or D since we have zeros there. So in this case, it's not an absorbing stochastic matrix, even though it has an absorbing state. In fact, it has two absorbing states. Whereas in this case, this would be an example of an absorbing stochastic matrix. It has two absorbing states, and we're also able to get to those absorbing states from state C. All right. So these absorbing stochastic matrices are also matrices that have a long-term trend associated with them. All right, so with the absorbing stochastic matrix, we can rewrite that as we have the identity matrix in the upper left-hand corner, the zero matrix in the lower left-hand corner. This is my matrix S, and this is my matrix R, my submatrix S and R. All right, so we have R is going to be a single element. Oh, there we go. So we have 0.5, and S is going to be a 2x1 submatrix. All right, so in the fundamental matrix, so fund matrix is going to be I minus R inverse. All right, so the identity matrix for a 1x1 matrix is just 1 minus 0.5 in this case. So that's my I minus R. So we have 0.5 inverse, which again, when you just have a single element, the inverse is just going to be 1 divided by that. So you have 1 over 0.5, which is going to be 2. So my fundamental matrix is, again, just a single entry there, and it's matrix 2. So in the stable matrix, you're going to take that fundamental matrix, and you're going to multiply it by the entries in your matrix S, your submatrix X. And then 0 is going to be all along the last rows. All right, so in this case, the stable matrix is going to be the same dimension as my original, so it's going to be 3 by 3. We're still going to have 0. And then we're going to take 0.2 times 2, which is going to be 0.4, 0, 1. And then we have 0.3 times 2 is going to be 0.6. And we have 0, 0, 0. All right. So in the last section here is looking at game theory. All right. So yeah, so the first one here is looking at a game that's hopefully strictly determined, I think. All right. So yeah, so suppose that R and C play a game by matching coins. On each play, C pays R the number of heads shown, 0, 1, or 2, minus 4 times the number of tails shown. All right. So we have R and C. So they can either show heads or tails. C pays R. H minus 4 times the number of tails shown. All right. So if they both play heads, we have 2 heads shown and 0 tails. So C is going to pay R 2, whatever. Is it dollars? Yeah, we'll say dollars. All right. So again, this is looking at the payoff from R. So if C pays R $2, R is going to make positive 2. All right, if C plays heads and R plays tails, so we have 1 head shown and then 1 tail shown. So we have 1 minus 4 So C is going to pay R negative $3. So that means, okay. So C is going to pay R negative. So C pays R, the number of heads, that's 2. Yep. So then we have 0, negative 3. So C is going to pay R negative 3. So R is going to lose negative 3. Yeah. So yeah, so this represents the payoff to R. All right. So if C shows tails and R shows heads, we have one head and one tail again. So you have negative 3 once again there. And if they both show tails, then we have 0 minus 4 times 2. So you have minus 8. All right. So that is my payoff matrix. So we have 2, negative 3, negative 3, negative 8. All right. So then to figure out whether it's strictly determined, we're looking for a saddle point. So I'll use red for the row player. So to find the optimal strategy for the row player, you're going to circle the smallest element in each row. All right. Oh, sorry. Negative 8 is smaller than negative 3. And then you're going to choose the row for which that is as big as possible. So R should show heads. And then for C, you're going to circle the largest element, so the biggest element in each column. And then you're going to choose the column for which that is as small as possible. So in this case, since we have one that's circled red and green, that means is strictly determined. So R should play the first row and play heads, and C should play the second column and show tails. All right. So if a game is not strictly determined, that's when you have these mixed strategies taking place. All right. So yeah, so you have the payoff matrix. So I'm just going to call this A here. It is 8, negative 7, negative 3, 7. All right. So again, if it was strictly determined, so the row player again would choose the smallest element in each row and make the one for which that is as large as possible. And the column player would pick the biggest element in each column. So yeah, so you see how we don't have one that's circled both red and green. So that means that this is non-strictly determined. All right, so again, that means that we're going to have a mixed strategy approach here. All right, so to find the expected value for a mixed strategy, you're just going to take the row matrix corresponding to the row player strategy, multiply it by your matrix A, which is your payoff matrix, and multiply that times your matrix C. All right, so A, so is each player picks their strategies 50% of the time. So the row player picks row 1 50%, row 2 50%, and likewise for the column player picks column 1 50% of the time and column 2 50% of the time. So just flipping the coin each play. All right. So we have 0.5, 0.5, we have 8, negative 7, negative 3, 7. All right, so you have 0.5 times 8 is going to be 4 plus 0.5 times -3. So that's going to be 4 minus 1.5. It's going to be 2.5. So this is just going to be a row matrix, actually. 2.5. And then we have 0.5 times -7 plus 0.5 times +7, I think would end up being 0. Because 0.5 times 7 would be 3.5. And then 0.5 times -7 would be -3.5. So we have 0. So we have 2.5 times 0.5. So that would be 1.25. Yeah. Plus 0 times 0.5. So you get the expected value is going to be 1.25. All right. And same idea for the other ones. So the only thing that's changing is your matrices. All right. So you have R is going to be 1, 0. And C is going to be 0.5, 0.5. All right, so we have 1 times 8 is going to be 8, plus -3 is going to be, times 0 is going to be 0, so 8. And then 1 times -7 is going to be -7 plus 0 times 7 is going to be -7. All right, so you have 8 times 0.5 is going to be 4, plus a -7 times 0.5 is going to be -3.5. So we have 4 minus 3.5 is going to be 0.5. All right, so C here, we have 0.9, 0.1. All right, so we have 0.9 times 8 plus 0.1 times -3. 0.9 times 8 plus 0.1 times -3. So you have 6.9. And then we have 0.9 times -7 plus 0.1 times +7. So 0.9 times -7 plus 0.1 times +7. It's going to be -5.6. All right, so then we have 6.9 times 0.7 plus -5.6 times 0.3. So we have 3.15. All right, so the last one here, so we have 0.25 times 8 plus 0.75 times -3 is -0.25. And then we have 0.25 times -7 plus 0.75 times +7. So 0.25 times -7 plus 0.75 times +7. It's 3.5. And then we have 0.2, 0.8. All right, so you have -0.25 times 0.2 plus 3.5 times 0.8. Is going to be 2.75. All right, 2.75. All right, so the strategy that is most advantageous to R is going to be the one with the highest payoff value. All right, so in this case, that corresponds to strategy C. All right, and the last couple of questions here are dealing with finding the optimal strategies. So starting off with the role player. So if you have a payoff matrix with all positive entries, for the role player, it comes down to minimizing, and then you're going to minimize the equation y1 plus y2, subject to the constraints. So then for the role player, you're going to march down the columns for your coefficients. So you have y1 and y2 are both greater than or equal to 0. So that eliminates it to just A and B here. All right, so then you're going to march down the columns for your role player to get your coefficients. So you have 9y1 plus 3y2 is greater than or equal to 1. All right, so your constants are always going to be 1 for each of these. And for the minimize, it's always going to be greater than or equal to. And again, you just march down the columns. So you have 9y1 plus 3y2 is greater than 1, and then 5y1 plus 7y2 is greater than or equal to 1. And then for the column player, you want to maximize z1 plus z2. And here, again, we have they're both greater than or equal to 0. And then for the column player, you're going to march across the rows for your coefficients. So you're going to have 4z1 plus 8z2. And that's going to be less than or equal to. So whenever you're trying to maximize, most of the time your constraints are less than or equal to some constant. That's going to be less than or equal to 1. And then for the other constraint, we have 6z1 plus 2z2. It's going to be also less than or equal to 1 there. All right, here goes. Moment of truth here. Uh-oh. What do we got here? Let's see. Ah, simple subtraction error. Yep. So yeah, so I think I went too fast, as I'm wont to do. So yeah, so you have 16 plus a -5 is going to be positive 11, not -9. Yeah. All right. So yeah, so that's why they get 11 there. All right. But our process is correct. I just made a simple calculation error, as I'm prone to do, just as much as any other as the next person there. All right. Hopefully you found this helpful. Hope you have a lovely day, and I'll talk to you all later. Bye now.